Welcome to my presentation on energy-efficient digital beamforming and means of linear computation coding. The motivation for this talk is that in fully digital beamforming, matrix multiplications have to be performed at very high rate, and that can cause an intolerable power consumption. The traditional approach, the so-called rate distortion approach, is that you reduce the bit resolution of your matrix entries and then you require less power and less computations. In this traditional approach, the trade-off between resolution and signal to quantization noise ratio is the following. With standard quantization to binary numbers, any additional bit improves the SQNR by a factor of 4, which is 6 dB. Alternatively, more advanced is the so-called canonical sign digit representation. Here, every additional binary sign digit improves the SQNR by a factor of 28, which is 14.5 dB. In this work, however, we show that, how and why we can do much better for large matrices. The key step to approach that is to go from rate distortion coding to linear computation coding. In rate distortion coding, given a vector in k dimensions, we want to find an approximation of this vector with as few bits as possible, subject to some fidelity criteria called the distortion measure. In linear computation coding, however, given a linear function operating on a vector in k dimensions, we want to find an approximation of the function with as few additions and bit shifts as possible, subject to some fidelity criteria. Now, in information theory, this means we design a codebook and represent the vector, respectively the linear function, by pointers to, respectively, combinations of the code words. Let me first review the traditional setting. In the traditional setting, that means if we have an n times k matrix A that shall be multiplied with a vector, we decompose this matrix element-wise, and each element then gets decomposed into summands, and each of the summands is only composed of powers of 2. An example of that is given here. Here you have some 2 times 2 matrix, and you approximate it by a quantized version with signed powers of 2, and then for any additional summand, the average signal to quantization noise ratio improves. And here every additional summand gives 14.5 dB, because this is the canonical signed digit representation. Since everything works only element-wise, the size of the matrix doesn't matter here. Now, what I'm proposing here is to decompose multiplicatively. So instead of writing A as a sum of matrices with only entries being powers of 2, now we decompose it into a product of such matrices. Now, complexity-wise, this is approximately similar. In fact, it is even slightly less because we don't need to add the vectors at the end. Now, in digital beamforming, matrices are typically rectangular, and you cannot multiply rectangular matrices of the same size. So here we have to resort to a trick. So we multiply factors on the right, which are square, but those factors are sufficiently sparse such that the overall number of additions stays constant. Now, this works the better, the larger is the size of the matrix, as it's shown here. While in the canonically signed digit representation, every additional term gives us 14.5 dB, here in the multiplicative decomposition, the additional gain in signal to quantization noise ratio depends on the size of the matrix and is apparently growing constantly with the matrix size. So here for the largest matrix, the additional factor here actually gives about 60 dB gain. The question is now, how do we find a good representation? Well, there are many ways to do that, and I'm not claiming of having the optimum one. Here I'm just giving a pretty straightforward heuristic method that works the following way. you approximate every column of the target matrix by a column of some codebook matrix C and some weight matrix W, which forms the linear combinations in C. And then this all boils down to recursive sparse recovery problem with a constraint on the coefficients, which must be sine powers of 2. That is, of course, a suboptimum approach, but the advantage is that its complexity is not large. Its complexity is similar to the calculation of the pseudo-inverse, which in zero forcing beamforming you need to do anyway. Now, let me try to explain why this works so well. Assume this is the target vector you want to approximate. Now you look in the codebook, that means among the columns of your matrix C, your leftmost factor, to find that vector which is most closely correlated to the target vector AK. And then you scale it with the power of 2 to get an approximation as good as possible. But then, of course, some approximation error remains. And then you try to approximate this error again by that code word of the codebook matrix, which is most closely correlated to the error. You find a sine power of 2 as a coefficient, here the -1, and you get a new approximation error, which is smaller than before. And in that way, you go on. And in that way, the approximation error just gets smaller and smaller. The important point to notice is that whenever you put one new coefficient in the W, that doesn't mean that you need to add vectors when you calculate the whole thing. It means you just need a scalar addition, because you first multiply the matrix W to the vector, and then you multiply the matrix C to the result of W times the vector. So there is never any product calculated between C and W. And that is actually the point where the whole game comes from. This can be illustrated in this asymptotic analysis. Consider the target vector AK as shown here. Now you can decompose your error, your total error, into a distance error and an angle error. The angle error comes from the fact that the correlation is not 1, and the distance error comes from the fact that you cannot take the best orthogonal projection because you can only scale by powers of 2. For IID Gaussian codewords, the squared angle error can be easily calculated by right distortion theory, and the average squared distance error can also be shown by some straightforward calculations to be given by the expression on the slide. Now, if you combine the two, you find that for any addition you allow in computation, the total squared error is reduced by a factor of 3.6 if the number of rows of the matrix happens to be the binary logarithm of the number of columns. On the other hand, if you go for the additive decomposition, a single addition reduces the total squared error by a factor of 4, or 28 for canonically assigned digit representation. However, in the additive decomposition, you reduce the error of a scalar entry of the target matrix. In the linear computation coding, you reduce the error of all the components of a column of it, so of n components. Now, if you now account for that effect, so you now allow for n additions to reduce n components, well then in the additive decomposition, the improvement in total squared error stays the same, but in the linear computation coding, this improvement factor is raised to the power of n. And that's why the improvement is the larger is the size of the matrix. And for matrix size growing to infinity, this improvement grows to infinity. Let me now give an example of digital beamforming. Consider an antenna array setting with 512 antennas at the base station and at least 8 users out there with IID Rayleigh fading and an optimized rate parameter R. Then the number of additions per matrix entry, which we require to achieve the same signal to quantization noise ratio as in the traditional signed integer arithmetic is given in the table below. Well, traditionally, if you have 1-bit signed integer arithmetic, you need an addition or a subtraction, depending on the sign, per matrix entry. With linear computation coding, however, you just need 1/8 of that, 0.13 additions per matrix entry. And this improvement by this factor of 8 is pretty typical. That holds pretty much for all target resolutions. Note that here multiplications are not required at all, except for multiplications with powers of 2, which of course in hardware are no effort at all. This is just a wire shifting the bits. Yeah, and that brings me to the implementation. If you want to implement that, well, you would reconfigure an FPGA whenever the beamforming matrix would change. Sparse matrices do not pose a storage problem because you would not store the sparse matrix, but just the position where the non-zero entries are. In fact, you would not even require to store the positions in an FPGA. In an FPGA, the positions would simply be the wiring on your chip. I already have some preliminary results for VHDL implementation of linear computation coding, and that indeed saves at least half the logic resources required for the standard implementation of matrix factor multiplications for matrices of size 256. However, I expect further improvements by optimizing this matrix decomposition with respect to the properties of FPGAs, which has not been done yet. Furthermore, we even do not need all the full functionality of FPGAs. For instance, multiplication units are totally obsolete, and some other functionalities of FPGAs are not required either. So we could actually go a step lower to so-called coarse-grained reconfigurable arrays. Thank you very much for attention.